KW intersections. Just quickly wondering, whose is its first time today? Hoping you enjoy it and come again also next time. So the first speaker of today will be Michal Kononenko, and he will be talking about quantum machine learning. So he did an internship at the Institute for Quantum Computing, and he is currently back in school again, and he's studying nanotechnology. So, give him all.
Everybody. So before I start, how many of you guys have experience in quantum computing or read about it somewhere on tonight? Okay, goodbye. So as Mary said, I'm a third-year nanotech engineering student at the University of Waterloo. About a month ago, I finished up an 8-month internship at the Institute for Quantum Computing. And since I've been at this meetup for about 6 months, not really contributing, I figured this would be a good time to make my first contribution. So this is probably, I'm not sure how representative this talk will be of the other stuff, other than the other talks we have here. I think Mary will test that a bit more. But without further ado, let's start. So quantum machine learning, or how I learned to stop worrying and love the Hamiltonian. So, okay, we skip this part. So this talk is based on a paper from 2014 by Schuld. There's a link to it on the meetup page. And basically the problem that we're trying to solve is a clustering problem. Basically, given a set of feature vectors x, we want to minimize we want to get a set of vectors, cluster them into a set of vectors k, such that, and arrange these vectors k, such that the Euclidean norm of all these vectors, the Euclidean norm of all these vectors is minimized. Basically, we have so what happens is we have a bunch of boxes, we have some vectors that represent the center of these boxes, and the combined distance of all these the combined distance from all these vectors has to be minimized. Finding the global optimum of this problem is NP hard. So in practice, nobody looks for global optima. Instead, we have a whole bunch of heuristics that we use to try to approximate it. One of these famous ones is Lloyd's algorithm, which divides up your vector space, your data set, into a bunch of spaces, and it's essentially a three-step process. The first one is assignment. So if you have a set of vectors in the
just erase everything on there.
Erase everything on there?
Yeah.
Cool. So if we have a set, so for example, we'll be using a two-dimensional data set because the board itself is we'll be using a two-dimensional data set because the board itself is 2 dimensions. But if we assume we have some form of, if we have a whole bunch of blue vectors, if we have a whole bunch of blue data points that I'm going to draw into this region, and if we have a whole bunch of yellow points that I'm going to draw in this region, this is obviously this is going to be very dispersed. This is going to be a very dispersed data set, so our clustering problem is too hard. Basically, a candidate solution to this problem would be finding a vector somewhere here, finding a vector somewhere over here, which are our k's, such that their function is minimized. So the first step we would do if we were trying to solve this problem is assignment. So we take each of these points in our data set and assign them to one of their clusters, depending on their Euclidean norm. So for example, this vector is a lot closer to the blue vector, is a lot closer to our blue centroid than to our orange centroid. So we assigned it basically saying it's a member of that blue cluster. And we continue repeating that, we repeat that for the entire data set until eventually we have something like this. The second step of Lloyd's algorithm is to update our centroids. So now that we have assigned everybody to a cluster, we can now determine the centroid of this data set by looking for a way to minimize, by looking for the middle of sort of all these points. So if our original blue vector was somewhere here, we would take the, basically we take something like, we could take the vector sum of all these data points, and if we did this, we have a whole bunch of component vectors, which if we add up gives us a resultant vector, say this way, gives us a vector, say this way, and which would tell us that for the next iteration of this algorithm, we should move the vector, we should move this centroid over to here. So now that so we should move our centroid over there. So in that sense, we're trying to find the sort of center of that. We're trying to find the center of that cluster. And then the third step, iterate. So now that we have that moved into this, now that we have that centroid moved, then we go over that assignment step again. So if our data set was a lot, for example, less dispersed, so for example, we have a point here that we once assigned to the orange cluster, well, now that we moved the centroid from this point to, now that we moved that centroid from this point to this point, it might make a lot more sense to move its assignment from the orange cluster to the blue cluster. And at this point, we evaluate we calculate that this error function by summing all the norms from all the centroids, and we look for some kind of stopping criterion. We accept that there's always going to be some error, and if it goes below this, then we call our problem solved. So in terms of time complexity on this, disclaimer: I've done basically no formal education in computer science. So from what I've been able to glean on the internet, the assignment step has linear time complexity, and the update step also has linear time complexity. And in terms of distance calculation, and the basically most complex part, the most time-consuming part, is having to calculate all these Euclidean norms. You have to take all your components, take all your vector components. You have to square them, subtract them from your centroid distance, and then take the square root again. And if you have, it might seem it is relatively trivial in 2 dimensions, but if you imagine this being an n-dimensional data set, as your data set, as your dimensionality and your number of points increases, the distance calculations are going to get a lot more time consuming and a lot harder. So, can we go faster? So the question is, can we go faster? I'm going to say, sure. Let's build an ASIC. Let's strip out the operating system layers. Let's strip out all the program languages. Let's just go down straight to electronics, build a gate array, feed in our data, feed in a centroid, and see how quickly we can calculate and basically try to calculate it as fast as gate arrays will let us do. So for a vector of n dimensions, we need n centroids. So a vector of n dimensions to take the norm. To take the norm between 2 vectors, which are going to have n2 n sub. We'll call that alpha. So to calculate the distance between 2 of these vectors, we'll call this one m1, m sub 2, m sub alpha. In order to calculate the distance between these 2 vectors that are the same dimension, we are basically going to need, in the distance and the norm, we're going to need n subtraction operations. So we'll subtract these guys. Then we're going to need n squaring operations. That's going to square our relative distance. We're going to need n minus sums and the square root. And thankfully, if your computer is managing to run Linux at this point, like mine, we know this can be easily done with adders and with registers and all these circuits. So we have basically we have a Boolean algebra. What that boils down to is essentially Boolean algebra. So I've sort of come up with this stupid. So basically, it's the same truth table as everyone's seen. One thing I like to point out that's going to be relevant later as we go into quantum computing is that idea of node. Basically, I just say that that's a bifurcation of. Of a particular bit. So this is 0. This output is going to be 0, and if that's 1, then this is also going to be 1. You can do this in circuits. It's a linear operation, but we'll see as we go into quantum computing that just doesn't become allowed. That just is not allowed. So, sorry, spoilers. And so basically we boil that entire problem down to a gate array. We have a whole bunch of, we basically go as low as we can. Question is, can we go faster? Well, let's see what the actual physics, let's go down to the actual lowest possible level of physics that we can go to, and go down to Newtonian mechanics, specifically Hamiltonian mechanics. So, what classical Hamiltonian mechanics, or Hamiltonian mechanics is a reformulation of Newtonian physics that basically takes in your total energies, puts them into an operator called the Hamiltonian, and then which then becomes a function of your position momentum vectors. And by basically taking appropriate derivatives and evolving your system, you can evolve your system in time. So you add up in that case you end up with a Hamiltonian PQ. Sorry, it should be. So this will be your x vector, your p vector, and your time vector, and that's equal to the kinetic energies of your system, to all the kinetic energy of the system, and your potential energy in the system. And so x, then as you solve this in time, x tells you the position. X then tells you the position of all your particles in the system, and dp dt. And dx dt basically tells you all the velocities. You can discretize that in time, feed it back to some numerical simulation, and get time evolution. What's important to point out about time evolution, and this applies to classical physics as well as quantum mechanics, is that it's linear and it's bijective, meaning that when you end up solving these equations, you end up with a one-to-one mapping between your input states and between your input position momentum and your output position momentum. This kind of makes sense if you think this kind of makes sense in classical physics, because if you have a momentum vector, if you have some particle right here in a position x that's moving along with a momentum p, you don't suddenly see that turning into two momentum vectors after another time step. And the mapping is bijective because Hamiltonian mechanics is deterministic. So you can basically, if you know how the particle is moving forwards in time, you can also predict how it will move backwards in time in your system. So what does that mean for our Boolean algebra that we built out with our gates? Well, first of all, it means this guy can stay. Because we have this bifurcation of circuits, we can easily determine that if we measure this, if we measure the output of that node and it's 1, 1, well then we know that had to be 1 we have to know that had to be 1. If we measure it to be 0, it had to be 0. So unfortunately, I'm just moving between the projector now, but okay, so no, it's okay. Not also meets this criterion as well. So if we have a NOT gate, and we measure a 1 at the end of a NOT gate, we know that the input gate to that had to be the binary 0 state. The trouble becomes with AND gates and OR gates. Because if you look at a truth table of an AND gate and an OR gate, if an AND gate gives us 0, then we can't determine just based on the fact that we measured 0 here, whether we had a 0, 0 as an input, or a 0, 1 as an input, or a 1, 0 as an input. So this becomes a huge problem. This becomes a huge problem if we're trying to describe computing in terms of Newtonian physics, because we lose that bijection. So what we do then is we try to sort of modify. We modify our algebra, and this actually comes from a famous result from 1973 by, I'm tempted to say Bennett, but I'm not sure if it's the right paper. But the solution to this problem of nonlinearity is to basically add more bits. So this special design here is called. That brings us to one of the first universal gates. That's sort of going to be a bridge between our world of classical computing and our world of quantum computing, and that's the Toffoli gate. So the Toffoli gate is an example of a otherwise known as a control NOT gate. Basically takes in two control variables, and 1 output. It takes in 3 input bits, and outputs 4 input bits. So the important bit to note is that it will return, so if you pass in 0 to this target bit, that gate will only return 1 on the state if this bit and this bit are 1. So what we have is and that's shown in this truth table. So if these are both 0 and you pass 0 in here, it's going to return 0. If you pass 1 into there, it's going to return 1. So it's going to not it it's going to not it based on this sort of AND condition. And this turns out in this gate turns out to have 2 great properties, one of which is that it's linear. So if we look at the truth table, based on each of these output states maps uniquely to an input state. So we can determine what our input is given our output. And secondly, we can emulate our 2 to 1 bit or nonlinear Boolean algebra using this gate by picking which bits we provide inputs to and picking which bits we provide outputs of. For example, if we just pass in 1 1 into here, know that we pass in the 1 1 state, then this turns into a classical. Then just by sending, then this C gate, this sort of subset here, turns into a classical NOT gate. If on the other hand we pass 0 into here, and we pick these to be our 2 inputs, then this starts to behave like a classical. Then this output wire here is going to behave like a classical AND gate. Traditionally, normally in our 2 to 1 gates, we would throw all this information. Then we would end up throwing all this information away. But you go into this 3-bit architecture allows us to preserve that information and use it to map unambiguously forwards and backwards. So here are some quick emulations that came up. So you get AND gate, you turn that to a NOT gate, you turn that to an XOR gate. You can in theory build an entire computer. You can in theory build an entire computer out of this. So by adding in this idea of it's traditionally what they refer to it as garbage data. It's usually referred to as garbage because it's normally being tossed out during the computation. But by adding this sort of data in there, we can compute reversibly. So not only can we tell you what the result of your computation is, but we can also tell you what your inputs were. So that brings us sort of what's termed as creates a billiard ball computer, which sort of behaves halfway between a classical and a quantum computer, in the sense that each of our billiard balls, in terms of Newtonian physics, you can model that billiard ball computer as a bunch of particles that are moving around, basically colliding with each other. Those collisions are deterministic, and depending on whether they collide or not, you can get computation or not. I like to think of it as well as you can think of it also as, if you want to go really fast, then, well, we can shrink classical physics all the way down to an atom. We can do a nice thought experiment by trying to shrink this down to a single atom. So if we picture a single atom sitting somewhere that's then coupled to another atom, we can let our 0 and 1 state be represented by the fact whether that atom is vibrating or not. So if we set this atom and we set it shaking, its vibration ends up being coupled to this atom, and this atom's going to start shaking. This atom's going to start shaking as well. And if we set up a system like this, where we have let's say 3 particles on 3 springs, and we start this one shaking, and this one starts shaking, and they're just out of phase, we can stop them from, we can sort of stop these from moving and come up with something similar to an XOR gate. And we can come up with something similar to an XOR gate. So this one shakes, they're in phase, so as you move it, this one doesn't move, and it produces their gates. They're held together, I like to think about it as they're held together by electric fields, which then propagate at close to the speed of light. So I'd say, as far as classical physics goes, putting a single computer, putting it into single atoms is classically about as low as you can get, in terms of physical manifestation of computing. Has this made our original clustering problem faster? Well, the problem is it hasn't, because we're still encoding n information, we're still encoding n bits onto n classical bits. So it hasn't. So we still have to do all that linear. We still have to do all this linear calculation. We still have to do all these squaring calculations. We'd still have to run them classically, and the problem is we'd also have to. And the trouble is now we've also introduced all this garbage data and all this default data that's actually made our problem worse. So can we go fast? So the question is, can we go faster? So is there some way to fix this? Can we go faster? Can we somehow use all the stuff that I set up to try to make the complication a lot harder? Well, I'll answer that question with that question. Can we go down to the quantum realm? So in the quantum realm, so now instead of dealing with classical bits, we end up dealing with qubits, and qubits can be in any superposition. Can be, I mean, you've heard this a million times over. They can be in the 0 state, the 1 state, or any superposition of the two, provided that the probability of them is equal to 1. So traditionally, the state of a qubit is denoted by this funky-looking wave function psi. It's a vector, and we'll write that as 0, and we'll write that in Dirac notation as a superposition of these states, and we'll give it a normalization condition, alpha squared plus beta squared equals 1. So this may seem daunting at first, but basically all I'm doing is treating this as modeling this as a regular old vector in a vector space. This 0 vector can easily be represented by 1, 0, which would be a vector in the x-axis, and that 1 vector would easily be representable by a vector in the y-axis. The only condition you have to place on this is that these two vectors are orthogonal. So when you find the measure, you can distinguish perfectly between whether your system's in the 0 state or whether it's in the 1 state. An important result of this is something called Ehrenfaust's theorem, which basically states that these vectors, which are also eigenvectors, so these states which express it, will behave like classical bits, provided you're still in the same vector space, provided you're still in the same vector space doesn't move, provides some conditions. You can sort of treat these like classical bits. So solve your circuit for the 1 bit, solve that linear circuit for the 0 bit, and then build a superposition from that. The kicker comes from the fact that when you actually measure the state of, so the kicker comes from this, that when you measure the state of a qubit, you instantly, as soon as you measure the state of a qubit, the wave function then collapses into being exactly in the 0 state, or exactly in the 1 state. And traditionally this is shown by taking the dual vector, which is shown by taking the dual vector psi, which is equal to, which for our state it'd be this, or 1. So this represents the same state, but we've done an operation called integration conjugate. So in our model of quantum mechanics, we've taken the transpose vector. So our 1, 0 vector, if we have this 0 vector, our other 0 vector here turns into a 1, 0 vector, and then we have to have a star because we conjugate these variables. And then in order to do a measurement, we then multiply these two quantities together, which then gives us equals alpha star 0, 0 plus beta star 1, 1. And here's where this notation really comes in handy, because we have this vector, because when we're taking this 0, 0 multiplication, that's basically equivalent to taking regular dot product of two vectors. So because we've established this as the same vector, these vectors are parallel. So our result here is going to be 1. and these 1, 1 vector is parallel as well, so our result is going to be 1 here as well. And then these become magnitudes of alpha squared plus magnitude of beta squared, which is then equal to 1. So, which is then equal to 1. No surprise, because we've measured with respect to our state, because we've measured the state of our qubit with respect to the state of our qubit, and because our qubit is in a vector space, we basically said that our qubit is fully parallel to our qubit. Incidentally, this notation is called Dirac notation. This little thing here is called a bra. This kind of bracket is called a ket, because then when you take these together, you get a bracket, and that bracket becomes that bracket is basically equal to a validating document. Don't laugh at me, I didn't make this up. Some very smart Nobel Prize in your state. Apparently that's what you do to get a Nobel Prize. So the So what does that mean for our algebra? So now we've taken our our Boolean algebra, which was traditionally restricted, restricted to either alpha equals 1 or beta equals 1. So we've taken an algebra where alpha was restricted to 1 and beta was restricted to 1. We've taken that sort of two-state system, and now we've taken it to an infinite amount of states that are continuously expressible between our 0 and our 1 state in superposition. And we can actually do better than that because alpha and beta turn out to be complex numbers. So that's why I have to take this alpha. That's why I have to take this complex conjugate here. That's why this alpha becomes a magnitude. This alpha has to become a magnitude because you end up having complex numbers and you end up having these weird phases, and that's where a lot of the weirdness of quantum mechanics comes from. So now we move from a Boolean algebra to doing our problems in a Lie algebra. There's a set of mathematical groups called Lie groups, which satisfy a whole bunch of relations involving commutation. Basically, you can take sort of these. They're basically matrices. You can think of it as so in terms of Lie groups, they're groups in the sense they satisfy the group axioms, and their algebra is equal to the sum of all their Lie groups. So every state, and so I forget Hamiltonians or matrices, but the idea is that you have, instead of this Boolean algebra, you have this much more complicated, much more complex, and much richer Lie algebra. And you end up in particular for that single qubit plus alpha plus beta 1, you end up entering your vector space lies in this vector lies in the Lie group SU2, which is known as a special unitary group. And the generators of this group are the famous Pauli matrices. Sigma y equals 0 minus I 0, and sigma z equals 1 0 0 minus 1. And they're just matrices. Do regular matrix multiplication. If you do regular, the way you express, basically the way you manipulate quantum states, you apply an operator to them, which is a matrix, which is basically a mapping of one vector to another vector, which is done by a matrix, and then you have the identity, and then of course you have the identity matrix there for completeness. But so you end up with these four matrices, orthogonal matrices in your group, in your SU2 group, and then by taking any linear combinations of these, you express all the possible manipulations in your Lie algebra, which then maps all the possible states that your qubit can be in. This Lie algebra ends up being diffeomorphic to a 3-sphere, which I'm told is very complicated which I'm told is a very fancy sounding mathematical term for basically say you can draw it, which basically says that these sigma x, sigma y, and sigma z matrices are orthogonal, and there's a complete description of this group can be made in terms of 3 of these. so you can model it in a nice three-dimensional graph. So if you want to know all the states all the states available to your computer, do this to Ubuntu, all the states available to your qubit. Here you have this is known as a block sphere, and it shows every possible state that your qubit can be in. So here those two eigenstates that we have that are alpha 0 and alpha 1 each map to antipodal points mapped to a pool on this block sphere. And then X represents sort of all the superpositions that we have in the real component. And then as we have, because our alpha and beta can be complex numbers, we have rotation along, we sort of have an imaginary rotation in an imaginary plane as well. So that's where this Y comes in. So and another thing we put on is our normalization condition. So if you put on our normalization condition as well, where alpha squared plus beta squared equals 1, we restrict the radius of our quantum state to 1, because the radius of our quantum state vector begins to correspond to the probability of finding that state in the 0 and the 1 state. And if we restrict this length to 1 because we say it has to be in the 0 or 1 state, so the surface of this imaginary sphere then becomes is the set of all points that are expressible in a single qubit. So the magnitude of that projected vector is the square root of the probability outcome, and that's for a single qubit. To go out to multiple qubits, we end up taking tensor products of these. Qubits. So really, what we would see is as we go out to SU. So as we go out to SU2, if we take the tensor product of any matrix of any of this matrix in this SU2 the algebra, we end up entering the SU4 the algebra, which is going to have a similar set of these generators, except they're going to be 4x4 matrices, and there's going to be 15, and there's going to be 16 of them, including the identity matrix. So what we would basically have is our new state. So we would essentially have a state. If we imagine taking the state now if we end up thinking this is a 2-qubit state, we can have another state, say phi, equal to gamma 0 plus delta. I'll just use delta for now. Delta, it's not a direct delta function. That's just another complex number. So as we are going after this, and quantum physicists are going to butcher me for this, but we can take we'll take a dyadic product of this. So we end up with alpha gamma 0 0 plus beta gamma 1 0 plus all these. So we end up with this state, and because this is wrong in very many ways, this bracket ends up being omitted. So we have these. So we end up with 4 orthogonal states, which end up being. So when we have 2 qubits. So now that we have 2 qubits in our system, we end up with 4 of these orthogonal states, which are 0 0. We can measure them in the 1 0 state. We can measure them in the 1 1 state, or the 0 1 state. And that kind of makes sense if you consider, say, 2 of these. It behaves similarly to, say, like taking 2 regular vectors and thinking of the 4 possible states they can have as being both up, one of these down, and both of them down, provided they're both distinguishable. You end up with 4 of these states. And because quantum mechanics allows you to express any superposition of these states, we'll replace these with our regular coefficients, and we'll have alpha, beta. We'll replace these alpha, beta, gammas, and deltas instead of having products. We'll just replace them with regular complex numbers. And now we have, in our quantum system, we have 2 qubits, but we have 4 values that can be used, that are needed to fully describe the state. In a Boolean algebra, we would only be allowed to have only one of these values would be accessible, because either this one would be 1 and all these would be 0, this one would be 1 and all the other values would be 0. In basically when we look at our memory, it has to be in one of these. It would be in that 2-bit system we want to in one of these configurations. In a quantum mechanical system, we can have this in any 4 of these configurations. The kicker being, so we can have it in any of these 4 configurations. The drawback of this method is that as soon as we measure that quantum state, as soon as us or any other physical process that needs to know that quantum state now measures it, at that point it collapses into being one of these states. So if we're looking at a classical, classical memory, no matter how many times we would look at those 2 bits in our computer's RAM, they would likely always have the same 2-bit value until they were overwritten by something else. If you have a superposition of any of these states, in particular if it's an equal superposition, then as soon as you measure it, there would be a 50-50 chance that, say, it would collapse into this state, or it would collapse, or your quantum state your measured quantum state is this, and then your quantum state would become 1-0. So n-qubit states are created, they're not diffeomorphic. So because there's 16 matrices, 15 non-trivial ones, because the identity matrix is kind of trivial as a generally group algebra, these end up being diffeomorphic to a 15 sphere. So unfortunately I can't draw a cute little diagram like this for a 2-qubit system, because that would require living in a universe with 15 spatial dimensions. What we can do instead in order to represent them is we can flatten them into 4x4 matrices, which is kind of what I did when I took that dyadic product of the 0-0 basis vectors and I turned it into this 0-0 vector. So now if we consider an operator, so that way we can express any manipulations to qubit system now in a 4x4 matrix. As we go out to 3 qubits, then we have the same thing applies, the same principle applies, but now I have 8x8 matrices that have to be used in order to express these states. Because if I had a third marker, you would add another up-down state that you can differentiate between. So in general, we go out to n qubits, fully distinguishable system with n classical bits. We can encode that in log base 2 of n qubits that are in this superposition. So that means if we have 8 bits of classical information, we can write this onto 3 qubits. If we have 16 bits, we can write this onto 4 qubits. If we have 16 bits, we can write this onto 2dn. If you have 4 qubits can write 16 states, and we have this nice logarithmic scaling between our classical and our quantum computer. So now we look at what we have now is we've taken our classical computer, we've put it into a reversible that can calculate n means, we've turned it into a gate array, we've turned it into a reversible classical computer, and now what we've done is we've taken that vector of n classical bits, and we've mapped it one-to-one onto a much smaller superposition of qubits, which are all in this one state psi. So the question is, what can we do to these things? So first thing we can do is we can start applying phase gates to these things. If we go back to that diagram of the Bloch sphere, we can rotate that vector. We can rotate that single qubit. We can take that quantum state vector and we can rotate it any way we want. If we have a 0 state, a phase gate of 180 degrees would move it from the 1 to the 1 state, which would behave very much like a classical NOT gate. What we can also do is, in special cases, we can try moving it 90 degrees. We can move it 90 degrees. So instead of being 0 and 1, it becomes an equal superposition of the 0 state and the 1 state. Not only that, we can also rotate it in the y direction. And instead of being an equal superposition of 0 and 1, now we have an equal superposition of phase. We have an equal superposition of 0 and 1 in a complex domain. And that's when we try adding 2 states together, or when we try projecting this, that's going to make a huge difference at the end result of your computation. So that's where this gate comes in, the so-called Hadamard gate. It's a special case of phase gate that does this 90-degree shift. It's also referred to as the square root of naught, which is a very interesting concept if you're, traditionally the Hadamard gate is denoted with this H. It has one qubit input, so we have a psi in, and we have a psi out, which is one qubit going out, and this Hadamard gate applies a 90-degree, 90-degree rotation in the x-axis of that block sphere. So if we put in that 0 state, it's going to map to into 1 over root 2, 0 plus 1. It's going to map into an equal superposition of these states, and this has to be square rooted because if we take our dual vector, that 1 over root 2 is going to become a 1 over root 2 is going to have to multiply 1 over 2, which is going to give us 1 over 2, which is our equal superposition. But the idea is that this is a gate, this is an operation that on a quantum computer, they can only do on a quantum computer, that you would have to apply twice to get a knot. So, twice to get a knot. So, let that sort of, I find that kind of mind-blowing about quantum computing. So, what we can do, another part of our quantum computer is the Toffoli gate. So I mentioned earlier about that super complicated 3-bit, super nice 3-bit, 3 bits in, 3 bits out gate. You can build it reversibly with a classical computer, but it turns out, unlike AND gates or OR gates or typical gate models of classical computing, you can build this with a quantum computer. So, and I'm going to actually went ahead and did this on one of the tools that I'll show around, and you can build out that. And when it comes to time evolution, and then when it comes to evolving the system in time, you can do differentiation on the state and on the Hamiltonian. So once again, that's related to the Hamiltonian. So we'll take so if you take your total energy in the system, you take your potential energy in the system, mostly similar to classical physics, mostly similar to what you see in classical physics. To differentiate, so it says differentiation Hamiltonian, it really shouldn't. It's a Schrodinger equation. I'm sorry to anybody who's watching this in the future, but you get time. So at that point you get time evolution, which then we abstract out into our gate. So now we've gone from our classical computer to a classical computer to a gate array to a semi-classical billiard ball computer running on a tiny atomic system to a quantum computer that's now running on tiny atomic systems that are in superposition that we can't look at until our calculation is done. So how does this help us with our original problem of k-means clustering? And that's where this paper comes in. That's where this Schultz paper comes in. It gives a nice overview into this quantum state, and we have something called a swap. We do something called a swap test. So what we do is, in order to measure so now we go ahead and we abstract out our entire system of qubits, and we start looking at we look at the centroids between two vectors in our quantum vector space. So we'll call one of our vectors A, or let's call it X, which is going to be our feature set, which is going to be our feature vector. That's going to be encoded in log 2 to the n qubits, and we'll have a vector CK, which is then equal to our, which is then going to be our centroid vector. We're assuming that you can efficiently prepare this. We're assuming that you can efficiently prepare these states and that they're available to you for calculation. And so what you do is you run it. One component of this is you run it through a swap test. You run it through this gate called a controlled swap gate or a Franken gate with two Hadamard gates, with two of these square root of naught gates over here. So now if we have so what we do is we pass x into this value, we pass c into this value, and we pass 0 into this value. So what this is going to do now is as the 0 goes through, this Hadamard gate is going to flip it into an equal superposition of 0 and 1. And this ends up being a control gate, very similar to the Toffoli gate, where it'll only do its action if the state of that is 1. But now we're in a superposition of 0 and 1, so it'll do the action, and it won't do the action in superposition. So you can solve this basically for this vector. So if this vector is 1, then what it's going to do is it's going to swap the value. It's going to swap the value of x and ck. And if it's not going to do anything. It's not going to do anything on this. It's not going to do anything on this gate. So if I read this correctly, so running this swap test on the network, and I'm not leafing through this paper as a security blanket, I'm actually doing it very important. So as soon as we do that, then we measure this value of, then we measure this ancilla state right over, then we measure that zero state right over there. So depending on the fidelity between these two vectors, if you solve the system, you end up that depending on how similar these vectors are, the probability of getting the zero state is equal to half plus half times the raw ck ket x squared. So I'm getting this. So you end up with the result that if these vectors are completely orthogonal, then your probability of getting the zero vector is going to be half. If they're completely parallel, then this value is going to go to 1, and your probability of measuring a zero state here is going to be 1. And using that, and if we're using that, basically a paper referenced in the Schultz paper was able to use that ck vector as a representation of the Euclidean norm. And using this ancilla test, you can use this to measure. You can use this to measure the distance. You can use this to measure the Euclidean norm between these two vectors. So when it comes to so using that, we can determine how similar our distance vector is to our feature vector. And since we have log n qubits that are encoding n bits, we can effectively do this with space complexity in logarithm. We can effectively do this in space complexity with logarithmic time. So today we've taken our classical computer, we've decomposed it down to this gate array, we've decomposed it into this toy billiard ball model, built it back up to a quantum computer that has n states, and by using the swap test, we can measure the the orthogonality between these two vectors, and if we prepare this vector correctly, that'll give us back our distance. Even if we use the probability of getting distance, we can repeat this measurement multiple times, because the result of this swap test is just going to be having these vectors returned over, and there's going to be having these vectors returned. We can feed another zero state and get the probability of that, and that's going to give us and that'll give us more confirmation of a particular distance vector. So in terms of open problems in quantum machine learning, there's a whole bunch. So this quantum K-means clustering, which I have not done justice at all. I have not treated with any rigor. Best looking into the Schultz paper. So that's been one of the. It's a notable accomplishment in the field, but the field is still very young. That paper is from 2014. Another review is available from 2015. So this is still a very untapped area of computer science. One thing people are looking at particularly is quantum neural networks. Those are very much nonlinear systems where you're getting multiple inputs, multiple inputs and outputting one action potential in the most basic sort of artificial neural network. So seeing how we can take that, seeing how we can take those algorithms and translate them into reversible quantum calculations, seeing how you can run those on a quantum computer, that's a major open problem. Quantum decision trees are another major problem in sort of quantum machine learning and quantum data processing. It's one thing to have a classical, it's one thing to sort of have a classical decision tree that sort of branches off like this, but then we end up answering questions. Then we can ask questions like, well, what happens if I put that equal superposition state into this? I can go into both trees. I can sort of explore both options. And then if there's some interaction, say between this option and between this option, maybe not necessarily implication, but if there's some interaction between these options, I can catch that on a quantum computer and not be able to explore that in a classical computer in nearly as much time. This is also quite interesting as evolution probabilistic of Turing machines when you compare it to, say, probabilistic Turing machines. Probabilistic Turing machines can explore one of these trees simultaneously, but quantum computers can explore all of them and return only one on measurement. If you have some correlations, or if your decision tree later on, let's say your decision tree then branches into two common paths towards the end of it, you'll be able to find those two paths much more easily. You might be able to find those two paths much more easily using a decision tree than using a quantum computer and a classical computer. And another one that's the last section of the paper, is quantum versions of hidden Markov models. So there's hidden Markov. So there's some study into looking at, say, Markov. So looking into not just looking into Markov chains, but into multi-layered Markov chains. So this could be, for example, speech processing. The example is in papers, for example, a speech processing program that has both Markovian behavior in the sort of intonations and the sounds that I'm putting out, and has a Markovian model in the word parsing that I'm doing. So trying to predict what, if I'm speaking, both predicting what is the word I've actually said and predicting what is the word I'm going to say next, or what is the phrase that I'm meaning to say, and looking into how to deal with these in quantum problems is quite an interesting experience as well. In terms of general quantum computing, this is mostly what I did during my 8 months. I did very little theory, so that's why I completely brushed it off. But challenges in general quantum computer, we've made some assumptions. First of all, we made an assumption that we can prepare our state efficiently. That's not necessarily always true. If you have an equal superposition of both the 0 and 1 state, as soon as you look at it to check whether you prepare that state correctly, that state's going to collapse into the state that you don't want prepared. So we have to prepare that efficiently. So we've assumed that we can prepare it efficiently. Doing that in practice is kind of difficult. It's also why quantum computers are taking so long to develop. Another thing is the quantum RAM, the quantum RAM access memory. Very useful device if we could have it, because you could send, instead of having to send an address bits to a classical computer and pulling some bits out, you could send an address qubit and explore basically most of the RAM. You can explore both the RAM. You can explore a large part of the RAM simultaneously in superposition, and you could have you could use this to encode classical data as well on the actual RAMs. And finally, this last one, decoherence. Basically, we're not the only ones looking at these. We're not the only ones trying to look at these quantum states. As you evolve forward in time, if there's a stray photon going through the quantum computer, if there's stray electrons, if there's electric charge moving around, they're going to be quite interested in knowing what that quantum state is, so they can know how to move, so they know how to move appropriately through the system. And well, as soon as that measures it, that quantum state is going to collapse. And you're going to have to be able. That quantum state is going to collapse as well if that radiation leaks out, or the basically or if the environment learns about it. So trying to deal with decoherence issues, trying to get all the operations done in a timely manner so that we don't have to deal with this decoherence is another major problem that IPC is working on. So that's my very hand-wavy talk on what we have to do to take a k-means clustering algorithm in classical space and move it to a quantum computer. The nice thing about this is that IBM has recently released one of their quantum computer as well, which if I go here, which is then available over here. I think I put a link to this in the meetup as well. So if you want to play around, if you want to take qubits and you want to play around with with a quantum computer, IBM's put out basically one of their versions, a 5-qubit system. So don't expect GTX, and so GTX 1080 will still run faster than this. Baby steps. So you can run an ideal quantum processor where they'll just do all the processing for you, or you can look into, or what they've done is they've actually opened up one of their quantum systems, one of their quantum computers, over to the internet. You can put your program into a queue to have it run at a later time. So here we see that assumption again. So here's an example of a Toffoli gate, that Toffoli gate that I was talking about, that today I've implemented using 6 binary quantum bits in our system. We start out with a 0 state. So we start out with a 0 state in both of these. So this is going to start out with, this X state is a 180-degree phase shift. That's going to flip this from 0 state to the 1 state. And then this is now a C-naught. This is a C-naught gate. So it works exactly like a NOT gate, but only if this value is 1, is it going to work as a NOT gate. That's the Hadamard gate that I discussed earlier. And then we have a whole bunch more C-naughts and Hadamards. And then finally, we have our program concluding with a measurement of our qubit in the Z direction. And now, if I'm going to do this correctly, because these are both 0, and we start at 0 and initialize to 1, because this is 1, our measurement here should be 1. And if we simulate that, that's exactly what we get. That's what we get here as an ideal measurement. On the other hand, if I set to both of these states to, if I take both of these states to 1, and I run that simulation, then we see that that state has in fact flipped to 0. So this is a very nice tool that you can use to play around with quantum computers. There's a very good 5-part guide on working with qubits and quantum computers that also delves into some things like quantum error detection and quantum error correction. Very, very interesting stuff. I suggest you guys take a look at it. So that's my talk. Not very interactive, very hand wavy, but I hope you guys learned something. Thank you very much.